All right, so sorry, I actually got a phone call, and yes, I kept working on that last example. But if you want, I'll do that. I'll finish that in class if you're confused with how to go about finishing it. Let's work on class example number 3. Fran and Bernie have identical collections of vintage toy vehicles. Fran selects 2 toys from the 10 shown for display in her cabinet. Since the order of display does not matter, she calculates that this can be done in 10C2 or 45 ways. All right, so she just chooses 2, and she can choose any two of these any two vehicles from the cabinet in any 2 ways. Now Bernie selects 8 of them from the 10 shown, and he comes to the same conclusion that it can be done in 45 ways. Now explain in words why 10C2 is equal to 10C8. Well, if we select 2 toys and leave 8 of them behind, the number of selections doesn't really matter, right? Like if it would be the same as if I took 8 out, 8 out of the 10 out, and left 2 of them behind. We're going to end up getting the same number. Now let's use factorial notation to show that this is actually the case. So if I have 10C2, remember that what this means, 10C2, means that I have NCR, where n is the number of permutation, r is the number of times that it's occurring. So that would be equal to n factorial over n minus r factorial r factorial. And so what we would actually write 10C2 as is 10 factorial over 10 minus 2 factorial 2 factorial, since 10 is n and 2 is r. So this would be equal to 10 factorial, or 10 minus 2 is 8 factorial 2 factorial. Now let's look at 10C8. So I have 10C8 again, where this is equal to 10 factorial over 10 minus 8 factorial 8 factorial, which 10 minus 8 factorial is 2 factorial 8 factorial, which is the same thing. And if we were to calculate them out, they're both going to equal 45. All right, so algebraically, we're going to show that NCR is equal to NC minus R. And what we're doing is we're just explaining algebraically this rule, this general rule for our above examples. So I know that NCR is equal to, as I explained above, n factorial divided by n minus r factorial r factorial. And I want to show that the same thing, that these are the same thing, right? That this and this are equal. So let's look at n c n minus r. So if I were to put this into my factorial notation, then what I'm going to be left with is n factorial over, if I want to have n minus r factorial times r factorial, then this becomes my n, of course, and this becomes my value of r. Alright, and so what I'm going to be left with is n minus r, which is n minus r, and that's factorial, times r, which is n minus r factorial. This is simply equal to, if we were to simplify this in factorial on the top, we would get r factorial times n minus r factorial. The reason is because these cancel out, and I'm left with negative r factorial and n factorial. Oh, sorry, r factorial and minus. Good. And if we look at this, n minus r factorial is the same thing, which is kind of written backwards as NCR. Okay, let's look at this next example. During a Pee Wee hockey tryout, all the players met on the ice after the last practice and shook hands with each other. Algebraically determine the number of players who attended the tryouts if there were 300 handshakes in total. And so what we're looking for is the value of n. And if all the players shake hands, that means that, you know, a handshake happens between two people. And so n of c of 2 is equal to, there were 300 handshakes. All right, and so what we need to do is solve for n. Now we can rewrite this using factorial notation. All right, so this can be rewritten as n factorial over n minus 2 factorial and that is equal to 300. Now, if I want to solve for n, then I'm going to have to do a little bit of rearranging. Right now, the first thing that I want to do is kind of separate this 2 factorial. Now remember, 2 factorial is just equal to 2, just 2 times 1. And so if I multiply both sides by 2, so multiply this by 2, multiply this by 2, those terms will cancel out. I'm left with 600. So then I'll be left with n factorial over n minus 2 factorial is equal to 600. And just like we did in lesson 3, we can simplify this now. And so n factorial over n minus 2 factorial is the same thing as saying n times n minus 1 times n minus 2 factorial over n minus 2 factorial. And that's equal to 600. So those will cancel out, and I'm left with n times n minus 1, which is equal to 600. And what we're then going to be left with is a quadratic equation. So n squared minus n minus 600 is equal to 0. And if we factor this, I have n here and here. What two numbers multiply give me, let's go, so let's try 600 divided by 25. So 25 times 24. So we would have negative 25 and positive 24 equals 0. And since we can't have a negative number, we can just reject. So n is either equal to 25 or negative 24, but we can't have negative 24 players. So we have in total 25 players that shook hands. All right, next, polygons and diagonals. Consider circles with 5 points marked on their circumference. How many triangles can be formed using these 5 points? Write the answer in combination notation. Well, I have 1, 2, 3, 4, 5, and I can only connect 3 of them. So 5, C3. Answer is 10. Now, how many lines can be drawn connecting 2 points on the circle? Write the answer in combination as well. That's going to be 5C2, which is also equal to 10. And then we want to sketch a regular pentagon. So pentagons have 5 sides. And a pentagon, yeah, that's a pentagon there. How many lines can be drawn connecting 2 points on the pentagon, including the sides of the pentagon? Well, that's also going to be 5C2, or 10. And how many of these lines are diagonals of the pentagon? 1, 2, 3, 4, 5. 1, 2, 3, 4. So we have 5 diagonals. And then express the answer to 2 in terms of combinations. Well, I have my number of lines in this part. So in part 1, and I subtract the number of sides. And so you get 5 there. Now, how many diagonals are there in a regular octagon? So octagon is 8, so how many regular diagonals? There would be 8 diagonals in an octagon. And how many diagonals are there in a regular n-sided polygon? It follows, well actually, here we go, it follows this general rule. Alright, and so using this general rule, you can probably solve class example number 5.